Hello everyone. In this video I want to show you a GUI that I made in MATLAB for analyzing trusses, and you can of course use MATLAB coder and convert it to standalone application and use it in your statics classes. So this is a GUI, as I said, graphical user interface. And you know, GUIs will be removed from MATLAB in the future, so you can convert it also to an application if you want. So what do we do here? Here is the window that you're going to see the original truss and the deformed truss. These buttons are used to pass the inputs to the truss, the location of the nodes, right? The corners of the truss. Here, which two corners are connected to which. Here, the loads on the nodes of the truss, how they can move, or the restraints. And here is their cross section for calculating the basically the displacements, and as well as the Young modulus. So it's statics and solid mechanics together, basically, can be useful for those. If you don't know how to enter those values for each one of them, you can select each one here, click, let's say I don't know how the degrees of freedom should be entered. So I check this and then say get help. And it shows you a text and it tells you how you should be doing it. Okay, so you can get help for any of them. Once you click on each one of these and you enter all the matrices, the numbers, then you can click on solve, and then it shows you the forces in each one of the members, positive or negative. It shows you the reactions at the supports, and here it shows you the deformed version of the truss against the original one from a scale of 10 to 1000 times. So you can move this slider to the right to show it with a bigger scaling. And once you click on solve, again, it is going to show it at a bigger scale. Okay, so it's a very good application, and it's all written in MATLAB, as I said, and I'm going to share it with you. There are 4 files that you need along with some pictures. So there is the figure, there is the M file behind the figure, and there are 2 utility functions, truss point and truss solver. And here is the main figure M file, okay, the truss analyzer. This is creating the points of the truss, and this one solves the truss problem using finite element. Okay, so you know we can easily do trusses with finite elements. And if you watch my video on solving trusses in finite elements under the playlist Finite Element and Answers, you'll see how this problem is solved, and you can see the theory behind it. Okay, so you see here that the matrices are taken care of, right? And you multiply the stiffness matrix, inverse of that multiplied by load to get the displacement matrix. And once you have the displacement matrix, you can find the forces in them, and then you can do the reshaped version of the truss with a W, which is a size, which I will get, and that will multiply the displacements, right? Reshape it, and that is this number you get from this slider to show the truss with the amount of magnification that you want. So what is the figure? The figure is this. As you can see, there is a push button here. There is another push button here. There are 6 of them here. There is a slider here. There is an axis here. There are 2 dynamic texts here. There is a static text, static text, static text, and these are button groups, these 2. Okay, so very simple. Again, static text, and static text, and in each one of them you click. So you see, for instance, this one is what? This one is push button 11. So if you go under push button 11 in the code, you can find what it does, right? So if you go to push button 11, let me take you there, right? So we need push button 11 should be this guy. You see, so what it does, it takes the values from handle's value 1 value to all the values 6, and these are those 6 buttons that you click on, these guys, to get your to input the values for the truss. You get all of those, and you can store them into GUI data. And then you see here, once I have those data, I pass them to the truss solver to give me the forces, to give me the displacement, and to give me the reactions. Here you see I use my magnification factor, which is a number from 10 to 1000. And then I form the truss points. And now I go to the main axis, which is this guy here. And on that one, I plot the truss and the original version of the truss, and I put the reactions and the forces onto those other text 8 and text 9, which are these two. Okay, so each push button does something for you. Okay, or let's say the push button for these values, like look at this one. This one is called push button 2. So what does push button 2 do when we click on it? Push button 2, let's go and find push button 2 here. So it gives you a prompt, okay, and with the title, and then creates the input dialog window. I have a video about this on my MATLAB playlist. You can see that with that prompt and with that title, and then waits for you to enter the nodal locations, store it in coordinates, this coord variable, and then store that coord variable under GUI data. Under handle's value 1, it stores coord, right? Or the other one, again, gives you another input dialog box. It gets the value load and stores it under GUI data dot value 2 and then value 3 and so on and so forth. So you see all of these value 1s to value 6, they are all basically taken from those inputs. So finally, when you come here, right, you can basically get those value 1, 2, and they are cell, so you convert them to matrix. And then those matrices are in strings, so you convert them to numbers, so you can use them and pass them to the truss solver. When you push on that help button, of course, it is basically it is going to see which one of these checkboxes you clicked on. It gets those and then appropriately show you a dialog box, right? So look, here is called push button 17. And these checkboxes, they have their own name, checkbox 1 to 6. So here, if we go to 17, push button 17, here, you see, it says, hey, get the values of those checkboxes. If help item number 1, which means if the first checkbox is checked, then show this message box, this long message. If the second one is checked, show the bottom message, second message, third message, fourth message, fifth message, and sixth message. Okay, you see? So this is the essence of this, and the major function, as I said, is this truss solver. So now if you click and run this test analyzer or run the figure, either of them, you get this guy here. Okay, let me do it for you. So here you can run either that one or this one, and you get this beautiful window. And now let's work on a truss example here. Okay, so this is the truss I have. It has 5 nodes, 7 members. Each member is 1 meter in length. The cross section is 10 centimeter by 10 centimeter, or 0.01 meters squared. The Young modulus is 8100 megapascal, so the members are made of a type of wood here. So this is a wooden truss. And let's say a person of about 100 kilogram or a little bit more is standing in the middle. So on the middle node, you have 1000 Newton downward. And in this system, we want to know how much is the force in each member and how would the truss move or deform after applying this force with all these geometric patterns. Okay, so here we need to put our origin somewhere, and so I go with basically the left node, right, node 1. So I go ahead and assume that this is our origin right there, and another one right here, something like this. Okay, and so if that's the case, then node number 1 is going to be 0, 0. And by the way, the coordinates that you provide here are x, y, and z. So there is also a z here. And in this case, since it's a planar truss, we can assume all z's are 0. So this app, that's right, it can do 3D trusses as well. It doesn't need to be a 2D truss. This app is capable of doing a 3D truss for you. Okay, the only thing is here, when we have under push button 11 here, I assume that your truss is 2D, so I use view 2. If your truss is 3D, you need to come here and change this 2 to what? 2 to 3. So use view 3 for 3D trusses. Okay, make sure that you change this line. And if you want, you can look at those coordinates. If the z of those coordinates, because this z is going to be a matrix, if z is that, then you can basically use view 3. So you know what, let me do it myself so you don't have to modify the app. Okay, so you see here, I say go look at the third column of coord, get the absolute value because some points could have negative z, and look at the maximum value. If max of ABS of coordinate third column, max of all z's is 0, then all z's are 0. And that means use view 2, else use view 3. Okay, so here I added a little bit of code, so it decides on code to view 2D or view 3D, and you don't need to bother about that. Okay, so let's go ahead and with this specific truss, run our application. So here we click, and it explains to you, says at least, it tells a little bit that 1 row per node. So the location of the first node, remember it was 0, 0, 0, node 1, right? That's what this guy is. Node 2 is at x of 1, y 0, 0. Node 3 is at x of 2 and 0, 0, okay? So here we go, 1 and 0, 0, and then 2 and 0, 0. And then node 4 here, the x of it is 1/2. The y of it is 1 times cosine of 60, which is a square root 3 over 2. So it's 1/2 and a square root 3 over 2. And you can type that exactly. You can say square root 3 over what? 2. By the way, this is 0.5, not 1. And the z of that is 0, of course. And then the last node is at 1.5x, and then the y is the same, again square root 3 over 2, and z of that is 0. So these are the coordinates of these 5 nodes. Okay, that. Now we go to what? We go to the loads. So again, here should be x, y, z. So none of the nodes have any load except for node 2, and x of it, there is no x force, there is no z force. The y force is negative 1000 because it's in negative y direction. So for node 1, no load. For node 2, 0, negative 1000 and 0, and node 3, 0, node 4, 0, node 5, 0. Okay, you see 1 row per node. Then what? Then we jump to connectivities. Now, which 2 nodes are connected? We enter the node of the 2 sides of a line, a member, as 1 row. So which nodes are connected? You see 1 is connected to 2 and to 4. So we go here 1 to 2 and then 1 to 4. 2 is also connected to 3. 2 is also connected to 4. 2 is also connected to 5. Right here, you can see that 4 is connected to 5 and then 3 is connected to 5. Okay, so 4 to 5 and 3 to 5. And when you get the results of axial loads, that corresponds to this order that you are putting them in. So when later I show you the axial reactions, the axial forces in the members from top to bottom, the first one is for member 1 to 2, the next one is for 1 to 4. So you need to remember which nodes you are entering as first row, second row, and so on, or which members. This order will be preserved down there. And these support reactions are again based on the nodes that you entered. So it's going to be node 1, node 2, node 3, node 4, and node 5. Okay, now the DOFs is something you have to pay attention. If in a direction it can move, you put a 0 for it. If it cannot move in that direction, you put a 1 to it. And here is just displacement, no rotation. Okay, we are just considering displacements here. So node 1, if you look at it, it does not move along X or Y, and here nothing is moving along Z. Pay attention to that. Nothing should move along Z, otherwise your truss is not fixed. So all of the nodes should be fixed along Z. Node 1 is a pivot, so it doesn't move along X or Y or Z. So all of the degrees of freedom for that, you should type in 1, means all of them are fixed. Node 2, only Z of that cannot move. X and Y of that are free, so use 0, 0. Node 3 can slide along X, but not along Y. So X is free, Y is not, and Z is not. And node 4 and 5 are similar to 2. X and Y are free, but Z is what? Taken, so it doesn't move forward and backward. That's the degrees of freedom. Then the cross sections for all of the members are what? 0.01. So you can just 7 of that. Remember, you have 7 members, so you get it like that. And finally, the Young modulus also for all of them is 8100 megapascal. So again, you need 7 of that. If the members are made from different cross sections or different Young modulus, here is your time to enter what? To enter different numbers, and times 1 to the 6 because they were megapascal. Okay, so now I'm ready. All the information is there. It took them all. Now I simply say solve. There we go. The purple and a black. You have a black and a purple here on the top of each other. Okay, one of them, the black is original, purple is the deformed version, but here the deformation is so small you can barely see it at 10 times magnification. So I would rather what? Bump up the magnification a little bit and ask it to show me a little bit more. Now you can see some movement. Now I bump it up again. There we go. Now you can see this node is going down and this node is barely moving to the right. Let's bump it even more so we can see that. Okay, and now you can see it better. Let's go all the way up, and that's it. You see this point, if you zoom in, right, it moves a little bit to the right because it's a slider, and this point is going down a little bit to the right because of the load. These are the forces in the members. So member connecting 1 to 2, this horizontal member is 288. Okay, and these are standard units. And these are the nodal reactions. You see at node 1 you have 500. The X is 0. Node 2, 4, and 5 are free nodes, no reaction on them. And node 3, the roller is also 500. And that is very obvious. In this case, of course, the truss is symmetric. So each one of them will have a what? Will have a 1/2 of this 1000. So the reactions in this case should be 500 and 500. And the X reaction at the pivot should be equal to what? Equal to 0 because there is no external X force here. Okay, and again, the forces in axial members, you see them, this guy was 288, right? and those other ones too, right? So this one was positive, but let's say member 2, which was 1 to the next member was 1 to 4, the way we put it in, that is negative 577, right? So this guy here is what? Negative 5. This member is under compression, but this bottom member is under what? Under tension. So you see, it solved the truss entirely for you. You see these values. If you want, you can add a third window here and call that nodal displacements if you want. I can do that too. It's not really a big deal. If you want, I can add one here and call it nodal displacements. And you see here, it takes care of the whole thing. Or if you want this maximum magnification to be even bigger than 1000, you can easily go in the code and what? You can modify that. So all you need to do is this number here. You see, this is between 990. So if you want, I can go from 10 to 10,000. Then all I need to do is what? Make it something like this. Okay, now it goes between 10 to 10,000. Now, of course, you have to go back to the figure and change this guy, because right now this is 1000. So you need to say, hey, this guy corresponds to 10,000. Now you can go up more, right? Or as I said, you can basically make these guys a little bit smaller, right? Do something like that, and then bring this guy on this side like this. And you can add another window if you want. Let me do that for you. Here we go. I added one. So I added one text here called nodal displacement and another big window to show nodal displacement. And all I added to my code is this U that you get under push button. This U that you get, put it on that new axis, which if you double click on it, it is called text 15. So that's all you need to do. Here we go. So now I pass those numbers again one more time to it. Now you see these are nodal displacement. Node 1 does not move. Node 2 moves about 3.5 micromils, right, or micrometers, or thousands of a mil, 3.5 micrometers along x, and 2.2 micrometers along negative y, or 22 micrometers along y. Node 3 along x, it does move, along y and z doesn't. You should see here all of these last columns should be 0 because along z nothing moves. And node 4 and 5, of course, they move too. And here now, since I can go up to 10,000, now I can see better magnifications. Okay, you can see here now I can see it more magnified. So I modified it for you, and again, feel free to use this in your statics classes or solid mechanics. This can be very useful. You can export it to be an external standalone app, and you can run it even if you don't have MATLAB. So I'll put the zip folder download link under video description for you, so you can use it and learn from it. Thank you.